before I jump into the material for this lecture, I want to revisit an example I was discussing last time. I think there's well, I explained it one way. I'd like to explain it another way because it's important. So we discussed computing a reduced density matrix from, for example, this state. So here I had this state which was like 0, 0 plus 1, 1. And then the procedure to compute the density matrix on just the first subsystem, call it A, was that we first form this matrix from this state. So that's just psi, psi. And if I write that out using this expression, I'm going to get these four terms. So I get a 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1. And then when I want to get the density matrix on just A, I take the trace over the B system, right? And we computed that one way last time, but another way is to note that the trace, the partial trace, is linear. Okay, so I've taken this 1/2 outside of the trace. And then also using linearity, I've distributed the trace to act on each term separately, right? And then from here, I can use that, or let me just write this out slightly differently to make this a bit more obvious. So this 0, 0, 0, 0, another way to write that is that it's 0, 0 on A, and then 0, 0 on B, right? So actually, let me just look at this one term here. This partial trace only acts on B, so it doesn't care about this 0, 0 on A. It just moves through that. So I get 0, 0 on A, and then I get trace over B of this state on B. Okay. Now, remember that we said the partial trace was cyclic. So I can move this bra 0 around over to the other side so that this is trace B 0, 0, right? This is just 1, and the trace of a number is just the number again. So this whole thing is just 1, right? And I'm just left with just the 0, 0. Okay? So that means this whole thing was just 0, 0 on A. If I think about repeating that procedure here, I'm going to get a 0, 1 and a 0, 1, 0, 1 and a 0, 1. This is now going to be 1, 0, 0, 1. 1, 0, that's 0. Trace of 0 is 0, right? So now this is 0. So this term goes away, right? And I didn't really have to go through this line of thought once you've done it once. You're just noticing that the trace is going to have, it's going to involve an inner product between this number and this number, or this bra and this cat. So if they don't match, that term's going to go away, right? So here, if I look at this second entry, that's a 1 and a 0. Those do not match. They're going to go away. So that's gone, right? Here I get a 1 and a 1. So that's going to give me this inner product of 1, and I'm just going to be left with the 1, 1 on A, right? So then this density matrix, row A, is going to be 1/2, 0, 0, plus 1, 1. Right, those are the two surviving terms. Okay, so the same thing I said last time, but this is just a more efficient way to do it. Last time I was using directly from the definition. Okay. Questions about that? Okay. There's one thing I want to say about lecture 1. A little bit more about lecture 1. Well, let's just recall some formulas we had. So we said that if I want to compute, or I had measurements were described by sets of projectors, okay, where the projectors had to add to 1, or to the identity. And then when I make a measurement on a system described by some density matrix, my probabilities, pi, of getting outcome I is given by this trace of pi I against rho on A. Okay? Good. Some properties of the density matrix that I didn't write down last time, but that you should know are, properties. So first, density matrices are always Hermitian. Okay, so rho is rho dagger. You can check it from the definition. The proof is given in the notes. They're also positive. So that means, one way of saying that is that for all vectors psi, rho, psi is a positive number. And they also have unit trace. They're trace 1. So the trace of rho is equal to 1. Okay, so those follow mathematically from the definition. What I want to emphasize or go through more explicitly right now, though, is that these lead to an important interpretation or way of thinking about what the density matrix means. So let's see that. So this first property, that the density matrix is Hermitian, means that I can diagonalize it. So I can write rho as some eigenvalues lambda I, and some eigenvectors I'll just label by I. Okay. And then, so that's sort of using property 1. Using property 2, we learn that the lambda i's are always positive, right? Because I could, in particular, I could look at this number, and condition 2 says that's positive, but that number is just lambda I, right? And then from 3, we get that the trace of rho is 1. And if I insert this expression for rho, the diagonalized expression, in here, I'm getting that the trace, the sum over I, lambda I, that this thing is 1. Using the linearity of the trace again, that's, lets me pull this out. I get trace I, and then this is 1. So this is just sum over I, lambda I, okay, which we said was 1. Okay, so we have a set of numbers. They're all positive, and they sum to 1. They sound like probabilities. And indeed, these do actually have the interpretation of probabilities, so let's see why. So if I think about measuring my density matrix rho with this particular set of projectors, okay, I take the eigenvectors of rho, and I form the set of projectors from them. If I now make measurements here, then the probability of my different outcomes, according to this rule, right, is that probability of getting outcome I is trace pi I, which is now this II, right, rho. Using cyclicity, that's I rho I, or using cyclicity, it's the trace of that, but it's a number, so the trace of a number is the number. Okay, and then if I compare this expression to this expression for rho, that inner product is just going to pick out, okay, maybe let me call this I prime or something, I prime index. When I take this, I'm just going to pick out the ith term, and I'm just going to get lambda I. Okay? So indeed, these coefficients appearing in my expression for rho are probabilities, and they're the probabilities of getting this outcome if I measure in with that set of projectors. Okay, so the way we should think about the density matrix is as saying that the A system is in some probabilistic mixture of this set of states. Right, so it's in one of this set of states, but I don't know which one, and which one is determined by that probability. Okay. Okay, good. So let me stop there for a second. Questions about this interpretation, about density matrices, about the partial trace? We're going to start with the cryptography and start using this as a tool in a moment. Yeah. Yep.
And they follow like one norm.
So they're unit normalized, yeah.
So this seems like a classical probability.
Right. So I'm saying it is. It's like this quantum state is like a classical probabilistic mixture of being in some particular state from some ensemble of states. So it's like, yeah, this is a classical probability. That's right. Yeah.
So how can you extract like the quantumness of the states? Like measure, you have like even if the state is well defined, you have the probabilities of measurements, right? So how can this appear in the density matrix?
Yeah, it's not really apparent from the way that I'm showing it right now. I mean, the quantumness comes in that these are still quantum states. And this density matrix can still have kind of uniquely quantum properties as a consequence of that. But yeah, from the perspective I'm explaining right now, that's not apparent. So maybe we should just leave it there and come back to it. But yeah. Okay. Good. So we can get to our first cryptographic subject now that we have all these tools in this language for talking about quantum mechanics. So the first subject I want to talk about is something called the one-time pad. Okay. Right. Okay, so the goal here, we're going to think about two people, or two agents. We're going to call them Alice and Bob, and they want to do something. So the goal is for Alice to send Bob a private message using a public channel. Okay, so what do those words mean? Private message, public channel. Let's start with the public channel. Okay. So we have Alice. She's in her lab somewhere. And we have Bob. He's in his lab somewhere else. And Alice is able to send information to Bob. So maybe they can, or she can send out a radio broadcast or something like this. But there's a catch here in that we're going to allow some third party, call them Eve. Okay. This is Bob. There's Alice. There's some third party who's malicious in some way, who could intercept this message and steal it and keep it for themselves. Okay, and Alice has no way of preventing that. When she sends the message out, it's out in the world, and maybe Eve is going to grab it. Okay, so that's what a public channel is. And then we want to use this thing to send a private message. This is going to be a bit. So we're going to call it M. It's a variable. It could be either 0 or 1. Okay, so that's what we call a bit. So she wants to send M. She wants Bob. To learn M. But Eve to not learn M. Okay. And so as it stands, this seems difficult, right? Because if Alice just takes the bit and she sends it over the channel, then it might end up with Bob, but if Eve chooses, she can intercept it and learn the message. So this public channel by itself will not suffice to let us send this private message. We're going to have to add some other ingredient. Okay. So this extra ingredient that we add, it's going to have to somehow break this sort of symmetry that we have between Bob and Eve, right? Bob and Eve have the same stuff right now. They both can look at the output from this channel. There's nothing Alice can do to make sure that one gets something that the other doesn't because they're exactly the same. Right? So the way that we break this symmetry, or the extra thing that we give to Bob, is what's called shared randomness. Okay. And the way that we can think about this is some coin, some fair coin, is going to get flipped. The outcomes could be heads or tails, or we're going to label them 0 and 1. So the outcome from the flip is some variable r, which is a bit. And then we're going to send that bit to both Alice and to Bob. Okay, but Eve is not going to get the randomness. Okay, so then once Alice and Bob share this randomness, the procedure for sending this private message will be the following. First, Alice will compute a encoded message that we'll call M prime, which is M plus R. Okay, so this notation might be unfamiliar. What I mean is just the sum mod 2, right? So I mean, what this symbol means is that if I go 0 plus 0, I get 0. If I get 0 plus 1, I get 1. If I get 1 plus 0, I get 1. And if I get 1 plus 1, that's 0 again. Right? Okay, so Alice is going to compute that. And then she's going to send M prime over the public channel. And then Bob, assuming Eve doesn't intercept, and he gets this thing, gets M prime, Bob will compute M prime plus R, right? And Alice can do this because she knows R, and Bob can do this because he knows R. Okay. Okay. So this is our procedure, and what we need to do now is check that this works, right? And there's two requirements for this to work. One is that it's correct, which means that Bob gets the message, right? And the other is that it's secure, which means that Eve should not learn anything about the message. Okay, so why is it correct? To check correctness, we just need to check that the outcome from Bob's computation is Alice's message, right, is M. So Bob is going to compute M prime plus R. And recall that M prime was M plus R, right? So this is M plus R plus R. But R plus R is always 0, right? If R is 0, it's 0. If R is 1, it's 0. So this is just M plus 0, which is always M. Okay, so good. It's correct. Oh, no, the same coin gets flipped, and they both find out the outcome. But it's not, yeah, they have to start out with this. It's not sent via the public channel. That's an important question, or important point. So we're just saying they have this at the beginning, some way that I'm not explaining. Okay. It would not work to try and have Alice flip the coin and then send it over the channel because Eve might get the coin outcome, and we don't want her to have that. Okay. Okay. And the other thing we need to check is security, which means that Eve, when she intercepts the message, should not learn anything about M. Okay, so to check that, what I want to compute is the probability that M is, some value, given the value of M prime, right? So why do I want to compute this? Eve knows M prime. That's what she can get from the channel. And what she's trying to learn is M. So we want to say, what is the probability that M is whatever value given that you know M prime, right? Is this biased in some way, or does this just look totally random from Eve's perspective, from the perspective of someone who knows M prime? Okay. So this is probability that I get, or that the message is M, given that the encoded message is M prime, is exactly the probability that the randomness is M plus M prime, right? There's a unique value of the randomness that will relate M and M prime in any particular way, right? And then the probability that the randomness is any given value, right? So this will be just some number, 0 or 1. Probability that this randomness comes out to be whatever, 0 or 1, is always 1/2 because it was a random coin flip, right? So from Eve's perspective, who knows M prime, the distribution of M is just totally random, right? And hence, Eve hasn't learned anything about M. Okay. Okay, good. So that's what we call the classical one-time pad. It's a very old tool in cryptography. Spies in the Soviet Union and whatever would carry around books of just random numbers. And when they talk to people, they would encode their message with the random numbers using the one-time pad, this procedure. And then the receiver of the message would have a copy of the book, and then they could decode the message, right? And so long as these books never fell into the wrong person's hands, the messages were secure. Sometimes they did fall into the wrong hands, and then messages got broken, and okay, there's many exciting stories about this. But okay, so I'm going through this in detail because I also wanted to explain to you a quantum version of this. So we're going to talk about the quantum one-time pad, where instead of trying to send classical data, we're going to try and send quantum data, quantum information, over a public channel and understand how we can keep that information secure. Okay. Okay, so now. Okay. So now we, again have our Alice and Bob, and now they're trying to send some quantum state, say some quantum system A, which is in some state psi. And again, we could have some third party, Eve, intercept this message, and we want to make sure that Eve will never hold the quantum information on A. Okay. Okay, so again, the trick for doing this is going to involve shared randomness between Alice and Bob. So we're going to again assume that they have this shared randomness. And the basic idea that we might start with is let's try to encode my state by doing something like this. So let's pick some unitary based on our shared randomness and act it on psi and send that over the channel, right? And then the rough idea is that, well, since Bob knows R, he could pick the same unitary. So let's say, okay, this goes over the channel, the public channel. And then we could have Bob do UR dagger to whatever he gets, which will be UR psi, and he'll get back psi. Right, so this looks like it's clearly correct. And then what we want to understand in some detail is, is this thing actually secure? So it looks like it might be, because if Eve gets this thing and she doesn't know R, she's not going to know which UR dagger to apply. And so it seems hard for her to get back psi. But we want to somehow formally understand, how do we say that she really learns nothing about psi? How do we actually prove that this thing is secure beyond that intuition? Okay. Good. So let's go here. Okay. So the first thing we need to do to make this more precise is we need to figure out what set of unitaries we're going to be talking about, right? So the idea there is that we're going to have some set of unitaries. They're indexed by our choice of randomness. We want a candidate set for what set should we be selecting from at random. Okay. To motivate the choice of that set, it's helpful to use the following fact. So we're going to assume that A is a qubit, so it's a two-dimensional quantum system for simplicity. And a two-dimensional matrix which satisfies all the properties I wrote down earlier over there somewhere. It's Hermitian, it's positive, blah, blah, blah. It's trace one. Can be parameterized like this. Okay, where alpha, beta, gamma are real. Okay, I guess actually these sit in some particular range, but that's fine. This is general enough to capture all such 2x2 density matrices. Okay, And then we can recall these Pauli matrices that I wrote down last time. Okay. And if we stare at this for long enough, we might notice the following convenient fact, which is that row A can be decomposed into a sum over Pauli matrices. And that will look like 1/2 the identity plus beta times x plus gamma times y plus alpha times z. Okay. Good. So you see that the thing we're trying to hide, right, this density matrix, which records the information on A, can be expressed in a basis consisting of these 4 Pauli matrices. So perhaps a reasonable choice of my set of things to average over is to average over this basis. Okay. So we're going to make a guess here, and we're going to say that maybe the matrices I should average over are these ones. Yeah, okay. So there's 4 of them, which means that now we're going to need to have Alice and Bob share 2 bits of randomness, so that those 2 bits of randomness take on 4 different possibilities and let them jointly choose the same random Pauli matrix. Okay. Okay. To index these more easily, I'm going to use the notation that P0, like the 0th Pauli matrix, is the identity, and the first Pauli matrix is X, and the second one is Y, and the third one is Z. Okay. Okay. Good. Okay, so we have another protocol. This is now the quantum one-time pad, the protocol for the quantum one-time pad. It's 3 steps again. So Alice is going to apply the R Pauli matrix to the system A. Then she's going to send A to Bob over the public channel. And then Bob is going to apply PR dagger to the thing he receives, to A. Okay. Good. So correctness here, as I was sort of describing before, is clear. So Alice is going to do PR to this system. Bob is going to get it. He's going to undo PR. Clearly, he gets back the quantum information that Alice sent him. So that's good. Security is more subtle now. Okay, and we're going to have to invoke these tools about density matrices and partial traces and blah, blah, blah that we were learning about last time. So to show security, okay, so maybe I'll write, okay, correctness is okay. But let's talk about security. Okay, so the first thing that we're going to have to do is we want to describe everything that Alice and Bob are using or sharing, the states that they have, in terms of our quantum notation and our density matrix notation. So the first thing we want to do is describe their shared randomness as a density matrix. Okay, So how do we do that? I claim that the way we should write down this shared randomness is in terms of this density matrix that involves sort of two-dimensional systems that I'm calling RA and RB. And it's going to look like this. So there's a 1 over 4 R and RB. Okay, so why does that describe Alice and Bob's shared randomness? The comments? Ideas? Okay, good. Okay, good. Yeah, so R now, I said Alice and Bob are going to share 2 bits of randomness. So this is sort of shorthand. If you wanted to kind of write this out more, say there's 2 bits of randomness that we can call R1 and R2. And then there's a state that's like R1, R2, R1, R2. And that's on RA. And then R1 and R2 are zeros and ones. So yeah, this could be like 0, 0, 0, 0, or 0, 1, 0, 1, and so on. Does that make sense? Yeah. Oh, I'm asking if you can justify for me why this describes Alice and Bob holding shared randomness. Yeah, go ahead. Yeah, yeah. So, okay, so we had this interpretation of density matrices before, right? Which was saying that when I have this like sum over some set of states here, that the interpretation is that what you're holding is like a probabilistic mixture of the possible states here, right? So you should read this as saying that with probability 1/4, Alice and Bob, or like this state, RA and RB, is in the state R and R, right? And so it's like, it's saying with P is 1/4, we had 0, 0, 0, 0, tensor 0, 0, 0, 0. So meaning that Alice holds the string 0, 0, Bob holds the string 0, 0. And then, with probability 1/4, Alice holds the string 0, 1, Bob holds the string 0, 1, and so on. Right, yeah. Sorry? Oh, where's the message? I haven't written down the message system yet. I've only introduced the systems that describe the randomness. So there's some other third system here that I'm going to have to do in 1 second, labeled A, that I'm not at the moment writing down. Does that answer your question? Yeah, so we could take a trace here. We could trace out, say, RB. If you use the procedure I was describing, what you would find is that this density matrix with no RB would be just this state here. And then what's the interpretation of that? That says that with probability 1/4, Alice holds the string, each of the strings in this sum. So with probability 1/4, she holds the string 0, 0. Probability 1/4, she holds the string 0, 1, and so on. Yeah. Yeah. Yeah.
different R's, like 0, 1,
Yeah.
the same in both I, A, and B?
Yeah, so R ranges over like 0, 0, 0, 1, 1, 0, 1, 1. And the important thing about this sum is that the R here is the same as the R there. So we're summing over all possible R's, but they're correlated between here and here. Yeah. Yeah. Yeah, so you could think. Oh, sorry, I'll repeat the question. So the question was, how do we, how would we realize this in real life? What's the situation like physically? And this would be like, there's somebody, let's call them the referee or something, and they take 2 coins and they flip them, and they get 0, 0 or 0, 1 or whatever they get. They send that outcome to both Alice and Bob, and Alice and Bob store that, store those strings. That's what this is saying. Yeah. Yeah. So the question was, Alice and Bob share this randomness. Can they make measurements and obtain the same bits? Yes. So they could measure. Alice could measure this system in a basis like in this basis, and she will obtain, some outcome R. And one thing that this says is that if Bob makes that same measurement, he will also always obtain the same string. Yeah. Yeah. So this RA system is like itself a 2-qubit system. So this is a 4-dimensional basis because I'm varying over 4 things here. Yeah. So the question is, if I'm only sending 1 qubit, why did I need 2 bits of randomness? Or why am I talking about 2 bits of randomness? And it has to do with this fact that my 2x2 matrix is decomposed into these 4 terms. Yeah, and it turns out like you can't get away with any less. So it is not possible to send 1 qubit securely using only 1 bit of randomness. You really need 2. Correctness, you could use no randomness. You could just send it and you get it. But security, you need 2 bits of randomness. Yeah. Okay, so maybe I should keep going. I'll try and finish the analysis of this protocol. Okay, so that's our starting point. So we've described the randomness. Now I want to add in the message, okay, which was mentioned before that I should do. So when I add in the message, I now have, I should have some density matrix describing the 3 systems, A, the message system, and RA and RB. Okay. So initially, before I've done anything, if I'm just thinking about, my parties, they hold these 3 systems, what I should do is just add on the A density matrix as just in a tensor product with the rest of the stuff. So I just hold, or like my larger state is just described by this. Okay. Yeah. E-
Repeat, please repeat again.
Does the first density matrix works like a key for the communication in the classical sense?
yeah, so sometimes we call this string R the key. And we say that Alice and Bob share a key. And the key is used to encode and then to decode.
And the fact that the key was shared before
Yeah,
reflects in the fact that the Alice and Bob reads the same R in the
yeah,
inside the expression.
yeah, that's right. Yeah.
Okay.
Like before or after sending the message, shouldn't like
You guys should speak louder.
shouldn't like Alice and Bob have to share classical information about the key?
They do. So this is a quantum description. This is describing shared classical randomness in the language of quantum mechanics.
So
But-
we're like exchanging a few classical information for more quantum information.
Sorry, say that again.
We are exchanging the key, which could be classical information, for the qubit, which is like more quantum
Yeah,
information.
yeah, that's right. So even though they only start out with shared classical randomness, they're going to be able to send quantum information. Yeah.
So just a second. Wait a second and speak up.
So Alice will send the qubits to Bob, right?
Yeah.
So it will be done in a quantum channel, or it needs to send classical information about the system?
We should call it a quantum channel. It's something that's going to take some quantum state in and spit out the same quantum state on the other side.
Oh, okay. So the channel cannot be classical also, or it can.
No, it can't be classical. Yeah.
Okay.
Would you have more security if instead of sharing a bit, you share a qubit?
So if Alice and Bob start out with each of them a qubit that is in a special state, they can use it to send a private quantum message of 1 qubit. Or they can start out with 2 shared bits of classical randomness and use that to send 1 qubit of secure message. Both are equally secure,
Okay.
but if you have a quantum thing, you just have 1 qubit instead of having 2 random bits.
Okay, thank you.
So there's some some advantage. Okay, I should keep going, but I appreciate the questions. Okay, so now we have this. Let me rewrite this slightly. This is equally good if I move my sum. Actually, let me move the 1/4 out as well. So we're going to take the 1/4 out. We're going to take the sum out. And then we have row A, tensor, this stuff. Okay, good. Okay, so this is our setup. Now we're going to start doing the protocol and following what happens to our state as we execute each step of the protocol. Okay. So the first step is we're supposed to apply the Rth Pauli matrix. Okay. So that will transform me to the following state. Okay. So Yeah, I guess I actually didn't say this explicitly in the previous lecture, but if you take a density matrix and you do a unitary to it, it transforms like this. Okay, and you can think of that as like, you know, in the pure state case, in the case where rho is just formed by one vector, right? When I evolve the vector, it goes to u of that vector, and then the bra is going to go to u dagger, right? So this is going to this, and then that just turns out to be true generally, even when this was a sum over many pure states. Okay. But I won't dwell on that too much. Yeah, so this, I could have put a dagger here, but, oh, he was saying, well, where's the dagger? Because I said that it evolves to u rho u dagger, but the polys are Hermitian, so p dagger is p, so I just put p. Yep. Okay, so that's what happens after step 1. That's my new state. Now we do step 2, and we send this to, we send A to Bob. So that doesn't really have an expression here, but we can kind of keep track of it. So after step 1, Alice has this stuff, right? And Bob has this. And then, so that's after step 1. After step 2, I'm just going to write this in a different order. I haven't really evolved the state at all. I'm allowed to write this in whatever order I want, and I'm going to use that just to emphasize something. Okay, so now Bob has this, and Alice has this. Okay. Right? Okay, and then if we're thinking about correctness, right, the next step would be that we would use that Bob can see this thing, right? He can read off what R is. So he can then go and do, you know, P again, which will cancel these P's. And in the third step, I would end up with just row A here. Right? Okay, but we're not talking about correctness right now. We already kind of convinced ourselves that that was okay. So instead, what we're worried about is, you know, in step 2, what if actually Eve intercepted the message, and so she steals this part, right? So now Eve has this. Okay. What we want to understand is, you know, can Eve tell anything? Can she see what this density matrix PA was? Right? Okay. So Eve's viewpoint, the way that we should describe that is we should trace out, we should use our partial trace, and we should get rid of Alice and Bob's systems to be left with the description of only what Eve is holding. Okay. So what we want to compute, right, is P A at this stage. I don't know. This isn't the PA I started out with, so let's call it sigma A. This is the density matrix that Eve sees, which follows by tracing out RA and RB of this A, RA, RB density matrix. Okay? Okay, so I'm going to probably run into the question time a bit here, but I want you to try and perform this partial trace of this state. Okay, keeping in mind this procedure I started out at this lecture describing, where we can use linearity of the trace, we can use that it's cyclic to simplify things. and see what expression for sigma A you can come up with. Okay? So go ahead.
Can I ask a basic question while they do this problem? I think I missed some point because I was distracted in the beginning, but L is applies PR to A where R is fixed, right? R is like 1 or 2 or 3. So how come R is inside the sum?
So R was chosen randomly at the beginning. And so to Alice, R is fixed. She's learned what R is, and it looks fixed. But to Eve, R is some random thing that she doesn't know. And so we need to keep R inside the sum. So it's like I flipped coins at the beginning to determine R, and then I run this. And so there's different probabilities from that coin flip, 1/4 for each different outcome. And so, my whole thing is described as some, there's 1/4 probability that she did PR with R is 0, 0, and 1/4 probability she did it with 0, 1, and so on. Yeah, I don't know if that.
Okay, no, that's okay.
Here, it's okay. I'm gonna. Okay, so I'm going to keep going and try and finish this up before too long. Okay, so let's take the partial trace of this thing. So sigma A trace RA RB rho A RA RB. Okay. So using linearity, I'm going to pull out the 1/4. I'm going to pull out the sum. This trace doesn't see the A system, so this is PR rho A PR, and then the trace, RA RB of RR tensor RR. Okay, and then cyclicity means I can move this R over here and this R over here, and I get a 1 and a 1, and then the trace of 1 is 1. So we get this. Okay. Okay, so that's a lot simpler, so that's good. But it doesn't really tell us that this thing is secure yet, because for security, what we want is that Eve's density matrix, right, which describes all the outcomes of the measurements, experiments that Eve could do, what we'd like is for that thing to just not depend on rho, whatever Alice's message was. If it just doesn't depend on rho in any way, then we know that Eve just can't learn anything about rho. Right. Okay. No, the 4 is still there, actually. Yeah. No, because this is actually the trace of, like, yeah, just this state. This state is like a normalized quantum state, so it's trace 1. Yeah, or it's a, yeah. It's a matrix with like 1, 1 on the diagonal. Yeah. Is it okay if I go to the hour and 15? Yeah. Okay, so we're going to try and compute this thing more explicitly and see, if it actually depends on on rho or not. Okay, so let's do that. So let's we started out motivated by this observation that I could express rho as some linear sum over the Pauli matrices. And now I have another sum over the Pauli matrices. So it seems like a reasonable way to compute this might be to use that expression for rho in terms of the Paulis, right? So let's do that. So sigma is 1/4 sum over R PR. And then I have like identity over 2 plus beta x plus gamma y plus alpha z, and then PR. Right? And I can split that into 4 terms. Sum over R, PR, identity, which doesn't do anything, PR, and then a 1/2, right? And then, okay, 1/4 sum over R, PR, okay, beta x PR plus gamma over 4 sum over R, PR, y, PR. Plus, okay, alpha over 4, PRC. Okay. Okay, so then you can compute each term separately. Since I'm low on time, I'm going to ask you to do that this evening. okay? But I'm just going to compute the first one. It's easy. So let's just look at this first term here. This is 1 over 4, 1/2. PR, right? PR is unitary and Hermitian. So that's just 1, or just the identity, right? I have 4 different terms in this sum. They're all the identity, so this is just 1/2 times the identity, right? There's a 4 from the sum that cancels this 1 over 4. Okay. So if I'm being slick, which I'm going to be now, but you can do it more more fully later, you can say that, well, this thing is I over 2 plus some stuff. Let's see, can I be slick? Okay, maybe I won't be so slick. Okay, so the first term is I over 2. Let's look at one more term. Let's look at the second one. So I have beta over 4, sum over r, PR, x, PR. If I write that all out, I have the first r gives me the identity, so that's just x. The second r gives me x, so I get x, x, x. The third one gives me y, so I get y, x, y. Fourth one is z, z, x, y. Sorry, thank you. Okay, beta over 4. X is the identity, right? So this is x plus x. X and y anti-commute, right? So I'm going to move the y through the x, pick up a -1, and then I have a y times y, which is 1. So that's the -1, and I'm left over with the x after the y's cancel. X and z anti-commute, same thing happens. I get -1 x. X plus x minus x minus x, it's 0. Okay. Similarly, all these other terms are 0. Okay? All of this stuff is 0. There's no extra terms here. Sigma was just the identity over 2. That proves security for me. The reason is that this expression came out to be independent of what I put in, right? What Eve sees, which is sigma, has nothing to do with Alice's message, which was rho. Right. Okay? Okay, so that's it. I can take a few questions.
Why can we write what Eve sees like that? Like what does the trace there means physically?
Yeah, so we said that when I was introducing the reduced density matrix, I was saying that it's an object like sigma A, density matrix on A, is the object that describes the A system completely without reference to what else is going on in the rest of the world. So in particular, we said that any measurement that we want to make on A, I can calculate the outcome, or the probabilities of the different outcomes, just from the density matrix on A. I don't need to know the rest of the stuff, right? So this object completely captures like the outcome of any measurement that Eve can make, right? And we're saying that the outcome of any measurement that Eve can make had nothing to do with Alice's message, and therefore it's secure. Did that make sense?
But like what does the trace mean in this context? Like, can we relate it to some physical meaning?
Yeah, okay. So if you want to think about a physical process that corresponds to taking the partial trace, what you should think of is like throwing some systems in the garbage. So if I have a state on A, B, I have some systems in my lab. I have the A system and the B system. And then I take B and I throw it in the garbage and I stop looking at it. Then what I have left is described by the density matrix on A. That's the physical process that is tracing out. Yeah.
Hello. While learning reduced density matrix, we learned that if row A, if the reduced density matrix is a multiple of the identity, then the original system is maximally entangled.
Yeah.
I just wanted to know if you could say something about that, since you didn't talk about entanglement.
Yeah. Okay, from some other class on quantum mechanics, you learn that if this density matrix is what's called maximally mixed, so it's just diagonal, and the entries on the diagonal are all, well, if it's 2 by 2 matrix, 1/2, 1/2. That says that A is maximally entangled with the rest of the world. So indeed, here we are learning that Eve's system is maximally entangled with the rest of the world. Turns out it's not maximally entangled with RA, RB. There's some additional stuff out there somewhere that we never kept track of with which it's entangled. But that entanglement is never coming into this problem because because it's not with RA and RB.
First there, then I'll come here.
I just wanted to ask, so when we take the partial trace over the subsystems RA and RB, we throw in the information of the shared randomness into the garbage, like you said. So what Eve sees is just the sigma A matrix.
Yeah.
So I assume, since this partial trace is what makes the information inaccessible, if we, for example, let's say Bob has received the system, so the system with the row A. So now the two physical systems Bob has access to are the rotated density matrix and the RR in the RB subsystem.
Yeah.
So I assume if we only trace out Alice's part, then the extra term that we have in comparison to Eve's partial trace, it makes it so mathematically that doesn't happen.
Yeah.
So it does that.
Yeah, that's right. So, and you can see that more explicitly by noting that, if I trace this out, what you'll be left with is actually just a sum over this guy.
Yeah.
Okay. And Bob could, based on the value of R, go and apply PR dagger, which is PR, and get back row A. So maybe let me show correctness from in this language, right? So what would I do? So now Bob has this, right? I'm going to trace out RA because if I want to look at Bob's viewpoint, right? That will just get rid of this, and I'll be left with PR, row A, PR, tensor RR. Bob can then do PR again using this, right? He can look at this and decide which PR to do. That gets rid of this. Now this thing doesn't depend on R, so it comes out of the sum. So now it's row A, and then tensor 1/4, sum over R, RR. So Bob has row A. Bob has A.
All right, thank you.
Yeah.
So I didn't understand the motivation for using the Pauli matrix as the U operator, the
Yeah.
UR operator.
Yeah.
Is it because we know at the end it's going to work, or is there was another purpose at the beginning?
It's an inspired guess based on the fact that the P's are also a basis for row.
Okay.
So, you know, I need to average over something. I need that average to sort of be big enough to kind of mix everything together. Feels like averaging over a basis is like a reasonable guess. And then we're checking that it works.
Okay.
Yeah.
Thank you.
I had the idea that Alice applies the operator PR to the whole density matrix. So I don't know how exactly means that, well, the physical mean about putting indexes R that are inside the summatory. So I don't know how it works.
Yeah, it's hard to feel I'm not quite
Isn't
describing
it
this.
fair to say that Alice and Bob don't see the sum? Alice measures something, right? And therefore
Yeah.
Alice has some R.
Yeah,
So
yeah, yeah.
Alice and Bob, they don't see the sum. It's Eve who sees the sum, right?
Yeah, that's
So putting the sum is when you are describing Eve.
well,
For Alice, there's no sum.
I would say putting the sum is when you're describing sort of the whole thing, including Eve, or including a possible Eve. And then, but yeah, you should kind of think of Alice as like, yeah, Alice sees a definite R. Like Alice has knowledge of R, so she kind of lives inside of the sum in some sense, is one way that we say it. Yeah, so
Putting a sum is like imagining you are repeating the experiment many times, right?
yeah,
And you are
that's-
saying
that's
sometimes
right.
Alice is in R equals 0,
Yeah.
sometimes Alice is in R equal 1.
Yeah,
But Alice really doesn't see a sum, right? Alice is in 1. That's why you always put the bracket inside the sum, right? You never put...
yeah, that's right. That's
So
right.
it would be, putting a sum is like saying this experiment was, Eve has no idea of what R was measured, right? So from the point of view of Eve, there is a sum effectively.
Yeah, yeah,
But A and B don't see a sum, right?
yeah.
We can say the procedure is secure because the if's viewpoints don't have any information about the message, right?
Yeah.
Okay, so is any difference if we use more qubits?
Yeah, so if we use more qubits for the message, you're suggesting, yeah. So we could have taken A to be 5 qubits or something. If the state on A is like row A1, tensor row A2, tensor row A5, it's pretty clear that this procedure is going to work by just repeating it each time separately for each qubit. It actually also turns out to be true that it will work even for a totally general state on my 5 qubits, where I just I encode it by like just doing Pauli's you know, to each qubit separately. PR. Okay. So I haven't shown this, but it turns out to work. If I just repeat this procedure for each qubit separately, that will be secure. This average will still, like Eve's perspective, will still see just the maximally mixed state, just the identity, but just on more qubits. And yeah, everything works as before.
Go ahead. So even if Eve catches the message and independent of if she gets something of it or not, wouldn't the fact that she catches the message change it if she later wants to send it to Bob to not be perceived?
Yeah, so here, like, you could ask for, you could study a different scenario where Eve like intercepts the message, tries to measure it to find out what the message is, and then forwards it to Bob and hopes that Bob doesn't notice. Okay, that's a separate scenario that you could study. We're not studying that. We're studying a scenario where Eve either intercepts it or doesn't. And you know, when she intercepts it, obviously Bob's going to find out that she intercepted it.
Any other questions? Very good. It was nice to have many questions. So let's thank Alex. And have a nice lunch.
Vamos lá para o